if I take this, oh, I did want n. Thank you, David. So by the way, this is what I always tell my students and you guys. David would have won the coffee prize for pointing out the errors, but I will always make errors just to make sure that you guys are listening, right? So you guys should always catch my errors. That's a joke. Because math talks have to have bad jokes, right? So this is n. And this is, of course, just 1, right? That's this map here. So that's, and if we take this and we tensor with C star, we get exactly this, right? So we take this, we tensor with C star, and we get this. And so that means that if we go backwards and we dualize, we have m goes to z to the n plus 1. So there's our torus of Pn. So the torus of Pn is exactly the set of everything in z to the n plus 1 such that the sum of the coefficients adds up to 0, right? So that's our torus of Pn. So the character lattice. Sorry, the character lattice. So so that's the hint of how we're going to define the torus of a projective toric variety. So yesterday we saw 4 ways to define an affine toric. And so one of them was that if we had A was equal to sum m1 m sub n, s I think z to n, then y sub A is just equal to the closure of phi sub A of C star n. So contained. So this was one of the ways we define an affine toric variety. So the torus, we know the torus of Pn satisfies star over here. And so the idea then is that we have Tn for an arbitrary toric variety, what I'm going to have is Tn goes to C star to the S, goes to C to the S, goes to, this is a projection to P ds minus 1. And we define our projective toric variety by projective toric equals close up pi of phi of A of C star to the S in E S minus 1. So instead of closing it up in C to the S, we close it up in P ds minus 1, where I have this quotient map that I'm looking at PS minus 1 quotient. So that's the way we're going to define it. CS. Say again. CS minus 0. All right. So so there's a subtlety that arises. So this is the definition, but there's a subtlety. And I'm going to, before I sort of, well, I guess I'll do this first. So example 2.1.5, there's a subtlety. The point is that different lattices can give the same projective variety. So the first one we've seen before. So if we look at S to the D to T to the D, which correspond to lattice points D0, 0D. Everything else is in here, which is contained in Z2. We saw that this gives us either this is example or exercise 1.1.1, which one of the groups did yesterday, that gives us either an affine surface, y sub A, affine surface in C to the D plus 1, or it gives a projective curve, x to the A, rational normal curve. I'm going to write RNC for rational normal curve in E to the D. So this is, and in this case, the observation is that y sub a is just the affine cone. Let's call this rational curve C sub b. So this is just the affine cone over the right. So let's call this lattice A. Script A. On the other hand, can you guys in back, if I write down here, everybody can see when I'm writing down here, right? Guys in back, this is all good, right? So we could also take B equals 1 t to the d, which would correspond, of course, to the lattice points 0, 1 through d and z. And this also gives you, when you close it up projectively, this gives me the rational normal curve, x sub a, rational normal curve, and d. However, I mean, the lattices are visibly different. The other thing to observe is that when you look at the ideal of I sub, if we look at the ideal of the affine variety, I of y sub a, you can see it's not homogeneous, right? So visibly, if I use this as projective coordinates x0 up through x sub d on projective d space, then I have things in here that look like x to the x sub I minus x1 to the I is in the ideal, right? So I have inhomogeneous elements of the ideal. You guys are all with me on this or not? You should yell at me now. Say it again. B, yes, good. So like I said, always testing if you're awake, right? So y sub b. So what's happening here? And so this is what we now are going to have as our first theorem today, and I'll even prove a little bit of it. So we're going to get an analog of a projective version of the 4 ways to define an affine variety. So here's our theorem. Okay. So theorem, and this is 2.1.4 EF. So this is an abbreviation that everybody probably knows, but just in case, it's the following are equivalent. So 1, y sub a is the affine cone of x sub a. 2, I sub L. I'll remind you in a second what I sub L is I of x sub a. 3, I sub L is homogeneous. And 4, this is the nice one that's easy to test, is that there exists a U in N and a K in Z greater than 0, such that inner product of M sub I U equals K for all M sub I K, right? So these are 4 equivalent conditions, and so this is exactly what was happening over here, is that this ideal is not homogeneous. So let's do a little tiny bit of proof of this. The other thing I wanted to say is you guys should yell at me. I tend to start speeding up during classes, and I know that there's a lot of non-native speakers of English, so if I'm talking too fast, just like wait. Yes, question? Say again. This line. Yes. So here, the point is that here, C star to the S is sitting inside here, right? And then just like when we form projective space as a quotient, right? That's what I'm doing here, is I'm forming a quotient. I'm looking at CS minus 0, quotienting to get a PS minus 1. And I'm taking the closure of this all the way up in here instead of just in C. So I'm going to be in a small yeah. So I'm closing it up in, this is my X, yeah. So the pride is probably X. Is that good now? Okay. All right. I'm going to say what IL is in a second. Great question. So that's part of the, I said I was going to remind you, and I'll remind you now. So reminder, recall that we had this sequence, 0 goes to L, left exact sequence, goes to Z to the S, goes to M, where this map is sending the standard basis EI to MI. So my A was equal to M1 through M sub S. So I have a set of S elements in my character lens. So then an I sub L, by definition, was equal to the set of x to the alpha. This is multi-index notation, so this is x1 to the alpha 1, x2 to the alpha 2, and so on, minus x to the beta, such that alpha minus beta is in L, right? So alpha and beta are both vectors, but they're vectors that have all positive entries, or non-negative entries, right? So that's what this is. So alpha, beta are all have non-negative. So this is called the lattice ideal, okay? So now I'm not going to prove the whole thing, but I'm going to prove the interesting part. So the interesting part, or the cute part, I think, of this is 3 implies 4. So let's go over here. All right, so now I'm going to do something. So this is an assertion that a priori, it's going to be true, but it needs a little bit more. So when I say the weight of alpha equals the weight of beta, what I mean is something like, we had an example of something like, say, s to the 4th, s cubed t, s t cubed t to the 4th was one of our examples, right? So one of the things that was in here was something that looked like 1 here, minus 1, let's see, that times that, yeah, 1, something like this, right? So we had something like, if we were using projective coordinates x0, x1, x2, and x3, then we had something like x0, x3, minus x1, x2 was one of the elements of the lattice ideal. You guys are all looking at this, right? Yes, question? Yeah, so what I just did here was we had 4, 0. Well, let me make a little matrix of the exponents. 3, 1, 1, 3, and 0, 4, right? So in the kernel of this matrix, what I claim is if I take this and this, that gives me, you can see this and this gives me a 4, 4, right? And this also gives me a 4, 4, so 4, 4 minus 4, 4, 0. So this is just a vector in the kernel of this matrix, right? And so that's how I'm getting my alpha here, in this case, the alpha would have been, so alpha would be 1, 0, 0, 1. It's this piece, and my beta would be 0, 1, 1, 0, right? And so that's it. So, and I'm claiming, oh, since it's homogeneous, it has to, anytime I have a homogeneous polynomial, that means that each monomial has to have the same degree, right? So I'm saying that this condition means that the weight of alpha, I should say, the weight is the sum of the weight of alpha is the sum of the alpha i's. So in this case, it would be 2 for this example, right? So I'm cheating a little bit here, and the reason I'm cheating is, could it happen? So here's for a prize. I buy somebody a beer tonight. Could I have a homogeneous ideal? So homogeneous ideal means generated by homogeneous elements. But in that homogeneous ideal, there's an inhomogeneous element. So for example, could I have something like x squared minus y cubed? Could that be an element of a homogeneous ideal? I see a yes. Why? You wanted a beer. You're German. I could have just taken the ideal generated by x squared and y cubed, right? That's a perfectly good homogeneous ideal, and this is in that ideal, right? But it's certainly not a homogeneous thing. So there's a little bit of before I make this assertion, I have to say one little thing, and it's pretty easy, and that is that note that I sub L has no monomials. And this is easy to see. Why? This ideal, we know that the point P of all ones is in the image of the phi sub A of C star to the whatever. Right? You guys are all with me, right? If I take the vector of all ones in here and I look at phi sub A, then I'm going to get this vector that has. So the vector of all ones is in this, but the point is that if I had a monomial, if I don't know, x to the alpha is a monomial, it certainly can't vanish. Right? Because a monomial, when I evaluate it all ones, is going to be 1, right? So I can't have any monomials. So the point is that I has no monomials. And so this assertion is okay. And so since I have the weight of alpha equals the weight of beta, this means that if I have some L in my L, that means that L dot 1, this is not the point that I was dealing with. This is a vector of ones, has to be equal to 0, right? And that's just because of this observation over here, right? The weights of alpha and beta are equal, so if I dot, you know, this thing and this, I get a positive 2 and a negative 2, so I get 0, right? So this means that everything in my lattice has to dot to 0 with this. And so now we're almost done, and so the point is what? So we had our original little sequence. We had our sequence 0 goes to L, goes to Z to the, what was I using? Z to the S goes to M. So now, the first thing I want to do is I want to hit this with Q. So if I tensor this with Q, and I want somebody to object to me, I get 0 goes to L sub Q, goes to Q to the S, goes to M sub Q. Anybody want to object to why this would still be exact? Yeah, tensor is right exact. But what am I really doing? Think about it. When I tensor with Q, there's another way to interpret that. I've got a sequence of Z modules. What am I doing when I tensor with Q? I'm also just, there's another functor that I could use. It's localization, right? So if I just localize this at the maximal, at the 0 ideal, that's the same effect here. And localization is an exact functor, so this is okay, right? So if I view it that way, just localize at Q, then this is still exact. And so then, and now I tensor with Q, and then I apply POM Q of blah into Q. Now, for this guy, POM is left exact, but when I'm applying it with a fixed thing in this entry, which way is it, covariant or contravariant? If I'm fixing Q, so suppose I had a map from here to here, that induces a map from here to here, right? Because I just follow the thing. So with this, it's going to be contravariant, right? So left exact contravariant. So what that means is then, now I've got, when I do this, I get N sub Q, that's the, right, this guy, goes to, I'm just going to write it as Q to the S again, even though it's a HOM, I'm being cavalier, goes to HOM. So I have a sequence here, and the point was that because this L.111 is equal to 0, that means that in the kernel there's a map here, right? And in this map here, the 111 vector gets sent to 0, right? That's exactly what that is saying. That's saying that the vector of all ones gets sent to 0 as an element of the HOM, right? Because when I HOM it, I mean, that's just dotting with my L, so I get 0. But this sucker is exact. And so, by exactness, Star says, by exactness, there exists a n twiddle in n sub q such that n twiddle dot m sub I is equal to 1 for all the m sub i's. right? So that's exactly what this is saying. By the exactness, I have this. Now this n twiddle, you would say, well, but that n twiddle is in n sub q, but it doesn't matter. So then I can clear the denominators, and we get the conclusion. So I wanted to do this proof not because it's like super cool or anything, but I think it's enlightening in the sense that it gives you a feel for the sort of the interplay of the way that these proofs often work, which is you use properties of your lattice and everything else. So we're using properties, and really pretty discrete geometric properties, to go from this homogeneous condition to this. So all of these things. So this is a nice, easy to check combinatorial condition, right? This is easy to check combinatorially, and this gives us this, and everything is equivalent. So now I want to talk about affine charts. So the nice thing is that this part, if you didn't like that, you should wake up, because affine charts they're really, everything works in some sense. So a lot of what the remainder of today's talk is going to be is, the theme will be things work the way that you would like. So affine charts. So suppose that A is, as before, M1 through M sub S, contained in M, and we have a corresponding toric variety X sub A contained in P to the S minus 1 for our projective toric variety. And we let U sub I equals U of X sub I equals V of X sub I complement. So this is the standard. So we have the standard affine open cover of projective space, and we let A sub I be equal to M1 minus M sub I, M sub I minus M sub I, so out, M sub S minus M sub I, and Si is equal to N of A sub I. Then X sub A intersect U sub I is equal to Y of A sub I equals spec of C of S sub I. So this is almost exactly what you would hope to happen if you think about what happens for the standard affine open cover or projective space. The only thing that's happening here is that these these monomials that we're using, these lattice points that we're using to embed, we think of it being as analogous to the variables. And the standard, if we're using a standard open cover on one of these coordinates on U sub xi, our coordinates would be x0 over xi, leave out xi over xi, and then x sub s minus 1 over xi, right? So this is exactly the analog of those quotients, except here I'm just removing the corresponding. So that's let's do the proof. So the proof is pretty easy. So I guess, I don't know if this is I can't remember if this is a theorem or not, or it's just an observation, but let's work through it. So, proof. The torus of X sub A is contained in the torus of P S minus 1, which is contained in V of X1 through XS complement, which is certainly contained in X sub I equals U sub I. Right, so this is a tautological statement. The torus of projective space, all the coordinates are non-zero. That's contained in the complement of the coordinate hyperplanes, which is certainly contained in the complement of one coordinate hyperplane. That's not U sub I, right? So that's a tautological sequence there. Say again? Where did I lose? Yes? This was the, so the A sub i's are lattice points, and the n was the, instead of the z combinations, these are natural number combinations, right? And so those were the natural numbers. And that's going to be, right, we want some kind of an affine sum. All right, so for all I, is contained, of course it's contained in x sub a, and it's contained in u sub i's. And we know that x sub a is the closure. This is, again, tautological of t x sub a and p s minus 1. So x sub a intersect u sub I is just the closure of txa in u sub I. And the last bit of this is that we know on u sub I, our coordinates, just like we said before, our coordinates are going to look like x1 over xi. If I'm using the xi's as coordinates for the vector space, we got xi over xi. S over x sub I. So those are the coordinates on u sub I. So t of x sub a intersect u sub I is just given by the image of the closure of the map that t goes to chi to the m1 over chi mi of t chi ms chi mi t. And this is exactly the closure of this is equal to my y a sub I. So it's really just following your nose from the usual description of projective space and using the mi's as the analogs of the x's. So it's a nice description, right? So it gives us a pretty, and like I said, it means, it sort of follows our intuition that toric varieties are going to behave sort of like the simplest one, which is projective space. So the other thing that I wanted to say, and we're going to come to this later, is, here, let me put it over here. Think about how things patch together. Side, second talk. How do things patch? Yes, questions, by the way. So what is Tx? So Tx sub a, this is the torus of x sub a, but I'm intersecting with u sub I. So what's the, on my torus of x sub a intersected with the u sub I piece, what's the image? The image is the closure, so it's the closure of this map. So T is an element of the torus, and T gets set to this, right? Because these things are exactly the analogs of these, right? T is an element of the torus. And then I close this, right? So I close this up, and the closure of this is exactly my y of a sub I. That's how we fit it. Okay, so quick recollection, recall the convex hull of sum A. A is just the set of summation lambda I, mi, summation lambda I, 1, lambda I. So this is a set of all convex combinations of my lattice points mi and m. Then 9 is that if A is equal to M1 times S, take M and P. So I take a polytope, which is the convex hull of these points. Convex hull for A. My A's are all supposed to be curly too, and to address the objection the other day about curly A's and straight A's. Then X of A is actually just equal to the union of the avert of X of A. So what does this notation mean? So it'll be clear when I do an example. So here's example. Staying with that, the 4, 0, 3, 1, 1, 3, 0, 4, which corresponded to the lattice points that look like this. Missing. The point is that I can cover my toric variety not by using all the lattice points, right? Here I was using sort of all these guys, these U sub i's corresponded to all the lattice points. But when I take the convex hull of those lattice points, I might have had, I might have had 1, 2, 3, here's an example of a lattice polytope intersected with M. The point is that I don't need to use all these. I could just use the vertices. So I could just use these 4 lattice points to cover. And so if you think about it for this example, let's see why that would be the case. Well, if I work over here, and this was s to the 4th, s cubed t, st cubed, t to the 4th, when I look, here's one of the, so what I'm claiming is that I can cover it just by looking here and looking here. So let's look at what we get here. So here, what's my spec, right? So this spec of s sub I, this spec of s sub I is what? My s sub I is n of n hull of the AIs. So what I'm doing is I'm taking this thing, that corresponds to the s to the 4th. I divide everything through by it. So I have s to the 4th over s to the 4th, which is, of course, just, well, it's right here. S to the 4th over s to the 4th, s cubed t over s to the 4th, st cubed over s to the 4th, and t to the 4th over s to the 4th. And I'm taking just the spec of that, summing through, so I'm looking at c of this. Of course, this is just 1, which I don't need because I already have c. This is going to be t over s. This is going to be t cubed over s cubed. I don't need that because I can get it as that cubed. And this is t to the 4th over s to the 4th, which I also don't need because I get this, right? So the point is that my c of s, if you call this vertex 0, this is just equal to c of t over s. It's a polynomial ring in one variable, right? It's just affine space. So this is affine space. So the point is that on this one open patch where the first coordinate is non-zero, that what I get is a nice curve. I'm going to get by symmetry. You can see that I get the same thing over here. So the point is that what this actually, our analysis proves, is that we get the image of this. And each smoothness is local, right? This thing is smooth, the other thing is smooth, so the image is a nice smooth curve. It's a smooth, rational curve in P3. It actually has a name. It's usually called the rational coordinate. So again, why would we care about this? Well, at some point in time, maybe by the middle of next week, we're going to start computing sheaf cohomology. And when you first learn the definitions of sheaf cohomology, you learn check cohomology. Check cohomology, you take a cover, right? And then you take, the basic open sets, and then you take intersections of pairs and intersections of triples and yada, 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 right? So that's the check cohomology definition. Now, if I take the check complex becomes increasingly unwieldy as I have more and more open sets, right? And so if I can find a thrifty representation of my open cover, it's going to make my check complex much simpler. So that's one of the reasons that we might want to have a nicer, more compact description of the affine opens. Is everybody with me on this? That's why this is a good use down the road. So the other thing, I want to say one last thing about this example is, so somewhere in Hartshorne, buried in chapter 1, I don't know, maybe this is Hartshorne somewhere in exercise in chapter 1, he asks you to prove this example is not projectively normal. So let me remind you, projectively normal, the definition is, I believe David gave it yesterday, but just in case. So a projective variety, x sub a, well, not any projective variety, x a projective variety, is projectively normal, Pn, exactly when the affine cone is normal. There's another way that you could say this in fancy terms. It's that H1 of the ideal sheaf is 0 for all twists. So that's the cohomological way to characterize projective normality. And we'll see that too later on. But this is the easy definition. And so this is an example of a smooth, a nice smooth curve which is not projectively normal. So how could I prove that this is not projectively normal? This is what we want to use. So I'm trying to figure out ways to work in theorems that we saw yesterday. So here's a place to work in a theorem. So somebody, for another beer, I'm going to go bankrupt, right? And all you guys do is I saw the hand. Good, excellent. It's not saturated. So we know that that the affine cones are normal exactly when the corresponding summing group is saturated. This is not saturated, and the reason is that when I look at, you can see that 4,4 is in the in the summing group, but 2,2 is not, right? So this is not a saturated cone. So you guys got to keep track of who I owe yours to. So that's not. So now you've got an easy way to answer some of the questions of Mark. So we got about 10 minutes left, and I think that's just about right to get through some basic definitions. So the last 10 minutes is sort of the easy part. This is mostly just definitions and reminders. Any questions so far? And I think, so David's point is well taken. In fact, I think that a lot of the varieties that you see, I mean, so many of the examples that one sees in algebraic geometry are rational, and toric varieties are always rational. So this is one of the reasons. And it's sort of because I think that's, I mean, when you look at things like Veronese varieties, Segre varieties, these are all going to be examples of toric varieties, and they actually will also have a nice interplay with the theory of divisors. So section 2.2, polytope bases. So a polytope can be defined two ways. So polytope is two ways. So what is a polytope? One is either the convex hull, that's the set of all convex combination of a finite set of points, or dually a finite, a bounded intersection of a finite number of half spaces. Example. So the first example is you take a bunch of points in space, you take saran wrap, you pull it around it and pull it tight. So for example 1, I took the points, say, in 0, 0, 1, 0, 0, 1, and I take saran wrap and I pull it around, I pull it tight, and I take the convex hull of that, I get this, right? So that's a polytope, convex hull of a finite set of points. Or the other interpretation of this is that I could write this as this half space, here's the normal, outward pointing facet, inward pointing facet normal to this facet, right? So this half space intersect this half space, the half space here, intersect this half space, right? So, and it's bounded, right? So in general, if I just had an intersection of a finite number of half spaces, this is something called a polyhedron instead of a polytope. So the polytope means that you have this bounded edge. So there's two descriptions of what a polytope is. And then it's going to be a polytope is a lattice polytope. is P containing M is R in vertices N, right? So I have actually integral vertices. And then the dimension, so let's see, so the dimension of P, let's get this up there. Dimension of a polytope is the dimension of the smallest affine subspace. P. And then this, what do we want to do here? I wanted to say something about this. Recall that we had a facet presentation, recall that P has a facet presentation. Lattice polytope. So right now my polytopes are all going to be lattice polytopes, so I have a facet presentation as the set of M and M R such that the product of M with U sub F, this is the inward pointing, well, it's a facet form, and M must be a facet. It's really minus A sub F. Right? So all these are, this is the intersection of half spaces, right? So I have these facet normals here, and so these U sub F's are going to be things that are pointing in these directions, and then I have some A sub F. So that's just a bunch of half spaces. So that's the facet presentation. And then we say that P is full dimensional if MP is equal to the dimension of my M sub R. So an example of something that's not full dimensional would be something like we had this polytope, or David put up a polytope yesterday. So the polytope is this nice little triangle, or this triangle, but if I stuck it into a larger space, right, this is a three-dimensional space, and you can see this polytope is the intersection. I have three half spaces. I have this thing, and this thing, but then I also have to intersect it with the half space that's over here and the half space that's over here. So I'd have to have 5 normals. And in particular, you can see, right, this is a two-dimensional polytope with a dimensional. So this is not a full-dimensional polytope, which is kind of sort of obvious. Oh, and the other thing I wanted to say is this is called the facet presentation. So 5 minutes, and we have just a couple more little things to define for polytopes. Say it again. Where? These A sub F's? Yeah. I think so. I'll have to ask me afterwards. Let me think about it. I have to think about it. I have to even think about whether these facet normals are pointing inside or outside. So David says no. Not necessarily. You know what? We could do it. You know what? Maybe we take 2 seconds and do an example. Let's do an example here. So let's do it for this thing. So here, my facet normals, you can see, and let's see if these are inward or outward. So if we do the inward pointing facet normals, the facet normal here would be 1, 0. The facet normal here would be 0, 1. And the facet normal here would be -1, -1 for my facet normals. Those are the inward pointing normals. So let's see what the conditions would be then. Here, I need all my lattice points of the polytope dotted with 1, 0 to be. So this half space right here, this is, let's call this facet 1, U2, and U3. I'm sorry for the guys in back. I'm sure my writing is too small at this point. Okay, so but for U1, this condition is going to be inner product U1 with M is greater than or equal to 0, right? I want to be dotting positive to that. Here, this is the same thing. This is going to be inner product of U2 with M is that's greater than or equal to 0. So those are not particularly enlightening on whether AF has to be positive or negative. But here, the inner product of U3 with M has to be greater than or equal to what? So the line itself, this is, if I'm on this line, this is where, and it's in the polytope, so if I took the point 1, comma 0, that is in my polytope. When I dot it with this, I get a minus 1. If I take this point and I dot it with, if I take 0, 0, dot it, I get 0. So this looks to me like this has to be greater than or equal to a minus 1 here. So I was just calibrating here because I just had to figure out what side of the hyperplane things are on. So again, if I dot U3 with this point, 0, 0, I get 0. That's greater than or equal to minus 1. If I dot it with this point, which is 1, 0, I get a minus 1, which is greater than or equal to minus 1. So there's the facet presentation. So 3 last operations. You guys are trying to make me run overtime. Simple, simplicial. So definition, if P has P contained in R, P has vertices, P is a simplex. So a 0 simplex is that, a 1 simplex is this, a 2 simplex triangle, 2 or 3 simplex would be a tetrahedron. And so on. So, and then a polytope P is simplicial. Every base is a facet. Every base. P is simple. Every vertex lies on D facets. So an example of a simplicial polytope would be the octahedron. So this is sitting inside R3, and every face of the octahedron is a triangle, so that's a simplicial polytope. A simple polytope would be the cube. Every vertex lies on 3 facets, so simple and simplicial. And then the last thing I want to do is sums, multiples. So the sum of 2 polytopes is pretty easy. So I'm going to have some P1 and P2. I'm assuming they're in the same P1 and P2 that are in the same, both contained in the same MSRI, and the Minkowski sum. P1 plus P2 is just the set of M1 plus M2 with MI and PI. And there's a nice way to picture this. So if I took, say, a line segment like this, plus a square, what you imagine doing is pick some reference vertices and pin them together and then run it around. So if I take this and I superimpose this vertex on this vertex and then I just slide that vertex around, I get a picture like this. Now this is still sitting inside R2, so that's the thing is that when you visualize this, these are going to be all sitting inside the same ambient space, right? So I take 2 things, superimpose them, make this this example. Minkowski sum. Dilation, Kp is what you think it would be. It's just the set of Km and P. So this is just a scaling, right? And then the last thing, which is kind of interesting, so you should wake up if you've fallen asleep on me, is the polar. So the polar polytope. This is a polytope in N, so this is in the dual, and it's it's the set of U and N sub R such that inner product of u m is greater than or equal to -1 for all m p. And I'm going to assume this is contained in NR. I said that already. And whereas we need 0. So I wanted to say one little thing about the polar polytope. So there's a very nice interpretation of what these polars are. So the idea is if you take this, your original polytope, which sits in M, so if P is sitting inside M, we consider P cross 1 sitting inside M sub R cross R, which pictorially is going to look like this. So let's say that our polytope P is that 2 simplex over there. Now let's make it a cube. So here's free space. So let's say P is equal to this polytope. This is the origin. So here's the origin. And here's the point 1, 1. Yeah. Okay, yeah, fine. You're absolutely right. Nice. Zero's in the interior. So I have the origin in the interior. So pictorially what I'm doing here is I'm going to take this P and I'm going to stick it inside the hyperplane in a 1 higher dimensional space. So my P is going to look like this. You guys are all with me on this, right? So I've taken it, stuck it in there. And then what I do is I cone over the origin, right? So I'm going to cone over the origin. So that's a picture like this. And then what I do is I look at the facet, the outward point facet normals to this thing here. So the outward point facet normals, this thing is going to go like this and hit. And you can see that what it's going to hit is it's going to hit right here. And similarly, this one's going to hit over here. And so if I looked at the intersection, so this is, my drawing's getting kind of crappy, but if I look at this hyperplane downstairs at height equals -1, and I draw these coordinate axes there, then what's going to happen is these facet normals hit that hyperplane, and I just look at the convex hull. So what I'm going to get for the polar is this picture. So this is going to be P0. So I won't write that out, but this is the interpretation of the polar, and there's a nice interpretation, which is this is gives you duality. So if I polarize twice, I get that. And so these are polar polytopes. And these are going to have, as you might guess, nice roles to play in various sorts of duality. So I ran 2 minutes over. I apologize. Oh, question. Say again. Where? Last line. Last line up here. Kp. K is just, this is an integer. This is a dilation. So Kp is the set of Km for all M and P. So it's just it's the k-fold multiple of my product. So I just dilate. So if I had a lattice polytope and this was P, 2P. How I got this rule? You have to think about it. So that's I think one of the exercises. So, but the point was I wanted to tell you. So if you just work through it. From the definition, you'll see that this is solution. All right. Copy? I'm not going to buy you beers right now for those of you that I hope beers.